and thank you very much for inviting me to present you my work, which is done in collaboration between several universities and institutes. And this is the outline of my presentation. In the beginning, I will give you a little background on what is computational material science, what is molecular dynamics, why it can be necessary. Then we perform first simple simulations on melting processes. Then we move to our ultra-short laser pulse interactions with metals. And then I will present you what is how the molecular dynamics is coupled to a continuum description of eukaryotic dynamics. Then how to run molecular dynamics in multiprocessing mode, parallel programming. And then I will show you the main results on modeling of nanostructuring process, periodic nanostructuring, and if we have enough time, I will also show you how to include plasmonics into the combined atomistic continuum method. So these are examples of nanostructuring processes basically aimed on functionalization of material surfaces. That could be generation of array of structures resulting in the change of hydrophobicity of the material. Such array also can change optical properties of material, and for example, the surface of metal can become a waveguiding. Nanostructuring also used in micro-optics, in surface-enhanced Raman spectroscopy, in holographic labeling, and lots of other applications. In particular, in this presentation, I will show you the simulations of formation of a single nanobump, nanojet structures, and nanobarrier structures. We also consider periodic nanostructuring of metallic surfaces and how this nanostructuring occurs in a liquid environment. So first we must build the model for that purpose. Then we investigate the mechanism of this nanostructure formation so that understanding on the underlying physics, we can therefore design experiments for generation of surfaces with pre-designed properties. And finally, if we have, again, enough time, I will show you the mechanism of formation of laser-induced periodic surface structures, LIPS structures that can be obtained in different geometry, depending on the geometry of the pulse irradiation, depending on the particular cases, up to three-dimensional structures reflecting also the crystal structure of the particular material. So what is computational material science? In general, it can be divided to three large computational science areas. So the simplest probably and straightforward in application is a continuum simulations based, for example, on diffusion equation or wave propagation. This is an example of application of continuum simulations on temperature dynamics on a real microchip. This can be implemented in a straightforward way and performed on a single processor, resulting in fast, efficient calculations on the real dimensions. But when dealing with ultra-short laser pulse interactions, the temperature and pressure gradients developed in the solid can be extremely high, and the phase transitions can occur under a significant degree of overheating, and the size of new phase nuclei can be as small as several interatomic distances. Under such conditions, the crystal structure must be taken into account, and therefore the continuum description of phase transitions, especially non-equilibrium phase transitions, fails. Alternatively, we can use ab initio study, where the system of Schrödinger equations is solved for a number of particles, as it, for example, presented here, just a few hundreds of atoms of water molecule subject to find the electronic density for reactive surface. And because the number of operations scales as a power of a degree of freedom, which can be up to 7, these calculations are extremely expensive from the point of computational power. And that's why they are strictly limited to just a few hundreds of atoms and can be performed on small spatial and time scales. And if we, however, completely discard information about electronic structures, the Schrödinger equation can be simplified to classical equation of motion given by second law of Newton for each of the atom, and that's the molecular dynamics approach. So Here, the atoms, the system evolution is completely determined by initial position and velocities of each of the atom, and they are moving according to second law of Newton, where forces are determined from the interatomic potential. Basically, in general, all this approach can complement each other because they take different spatial and temporal scales. So as I said, if we completely discard information about electrons from the system, we arrive from Schrödinger equation to classical equation of motion. And the criteria for applicability of molecular dynamics for each of the material can be determined from the de Broglie wavelength if it's much less than characteristic interatomic distance. And that holds true for most of the materials except the lightest particles and those particles that expose high polarity, for example, water molecules. So this classical molecular dynamics approach, for instance, can be used to study melting process on the example of fabrication of nanoscale devices by means of laser-assisted direct imprinting in silicon. But as you can see, this is an example how the molecular dynamics looks like. So it's a system of equation in three-dimensional space. So for n particles, we have three n equations. And having the initial positions and initial value for the velocities, the evolution of such system will be completely determined based on the interatomic potential. And in order to integrate the system in time, we can use different integrators, for example, Verlet algorithm, velocity Verlet, very efficient but not very precise on a short time scale algorithm, or Nordic fifth order predictor corrector algorithm, which has a high precision on short time scale but a bit more expensive computationally. And the precision of calculation one can control by the energy conservation also. Energy of the closed system must be conserved. A straightforward application of molecular dynamics, of course, seem to be very expensive, since the number of operations scales as n squared, because the interaction of each of the particles and summation of all the energy takes a lot of computational power. And the system size in a straightforward application will be quite limited, up to 10,000 particles maybe. So let's see how we can increase the efficiency of these molecular dynamics applications. So as I said before, the forces, interatomic forces, determined from the gradient of interatomic potential, which is a semi-empirical function presented in this plot. So this is the interatomic energy of pair interaction depending on the distance. As you can see, the simplest Lennard-Jones potential has an attractive and repulsion part, and it has only two parameters. Sigma parameter reflecting the depth of the interatomic potential well, and alpha parameter is related to the equilibrium distance for the interatomic positions. And this potential is good for representation of dynamics of solid inert gases, van der Waals force calculation, and our system with FCC crystal structures. This is the example of FCC cubic cell. FCC structure, so it's atoms in the corner of cubic, and at each face one can see another atom in the center. This is a closed packed structure. There are no possibilities to place the atoms more packed than it is given by FCC structures. Ideally, the interatomic potential should represent all the material's properties, so the energy of interstitials, equilibrium positions, vacancies, behavior at high pressures, thermal expansion, because as you can see, if you add up kinetic energy, the equilibrium, middle position, equilibrium position of interatomic interaction will be expanding, so it reflects the thermal expansion process. But for different structures, one can propose different interatomic potentials. For example, to describe silicon structure, it is open diamond structure, so there are additional forces to support the angle between the interatomic bonding. That's only possible in description of the potential via adding three-body interaction term. If we remove it, the open diamond structure inevitably will collapse in FCC structure. For description of metallic bonding, one can account for many-body potential given by so-called embedded atom method. So the ions are moving in the cloud of free carriers electrons. And basically, why it is a semi-empirical function? Because one can construct manually, artificially, a lot of potential depending on the physics understudy, depending on the crystal structure one to want to reproduce. So it can be pair interaction, 3-body, 4-body, 5-body, and so on, up to Coulomb interactions as well. But number of parameters entering each of the potential are fit to reproduce the material properties essentially from ab initio calculations. So one of the properties that one can see from a simple potential is that at some distance, the energy of pair interactions goes very close to zero. And that allows us to introduce so-called cutoff distance, at which the particles located at larger distances can be discarded from the calculations, and that allows us to introduce so-called cutoff radius, only inside of which we can calculate forces acting on the particular particles. But of course, in order to create such a list of interactions, one still has to consider all the other interactions where the particles are inside of the sphere. But if we add up a skin layer to such the sphere, then calculating the list of possible interactions inside of outer sphere allows us to perform this operation not every time step, but every 10 or 20 steps. That increases a little bit efficiency of calculations, and system up to 100,000 of particles can be calculated with a single processor. And lately we introduced much more efficient linked list algorithm, which resulted in scaling of operations as n over 2. So basically it's done in the way that we divide our system to number of cells with a size just above the cutoff distance. And then in order to search to compose the list of possible interactions for a particle in the host cell, we only must consider neighboring cells without consideration of all the rest. This allows us to raise the number of particles up to 1 million, and this is an example of this method application as ion penetrating solid. So this is a top view of ion penetrating metallic solid. This is side view. So one can see that first ion deposits its energy fast within the cylinder of specific diameter, and then we have non-equilibrium phase induced transformations, including melting, spallation, evaporation, and the kinetics of these phase transitions is addressed with molecular dynamics. Of course, one can use a simple description of phase transitions given, for example, by Gibbs theory, invented yet in the last century. And it's, the kinetics of phase transition can be basically described from phase diagrams. This is a simple phase diagram of water. So it represents solid, liquid, vapor phase. Up to a certain temperature, only solid and vapor phase can exist. Then we have liquid, and then we can have critical point above which the phases are indistinguishable. In particular, we have supercritical fluid, which is highly compressible and has zero viscosity, so it can penetrate any pore of the material and so on. So, but the Gibbs theory can be represented in a simple way. So there is a Gibbs free energy function, which includes internal energy, potential energy, kinetic energy, and it says that if the Gibbs free energy of liquid at some temperature becomes lower than Gibbs free energy of solid, then it is energetically favorable for the material to have a phase transformation from solid to liquid. However, in reality, it never happens at this point, because in order to develop new phase, one has to add even more energy, so that the nucleus of new phase must appear and then it must grow, overcoming the nucleation barrier. Depending on the presence of points of nucleation, that can be, for example, surface or defects. The difference between Gibbs free energy of liquid and solids at which we have phase transformation is different. If we don't have any centers of nucleation, then this Gibbs free energy difference may be significant. So there are more complex phase diagrams. For example, this phase diagram for iron representing its different crystal structures, body center cubic, phase center cubic, and so on, vapor phase. But the kinetic of phase transition can be still studied here in the assumption of equilibrium. But there are more complicated cases. For example, this is phase diagram for copper chromium alloy, and it also has can have normal phase transitions. For example, this is a condensation of vapor to liquid, which can be described in continuum as well, and this is molecular dynamic representation. But there are situations when we have metastable or metastable state or resulting in non-equilibrium phase transition. For example, so-called spinodal. If at a certain percentage we lower the temperature, the alloy can no longer exist, and without any nucleation barrier, it's spontaneously decomposed to different metals, to different compounds. This is the simulation of this process. So that's why the molecular dynamics can address the kinetics of such non-equilibrium phase transitions at atomic level, and the phase transition kinetics can be studied with the help of molecular dynamics. So, but before we study, we first must understand what are the material properties reproduced by the chosen interatomic potential. It is necessary to have the results of our simulation quantitatively defined. So the most interesting point for us is the melting point, whether it's represented by the given interatomic potential or not. The melting point can be defined in the sequence of liquid crystals coexistence simulations at the equilibrium. Liquid crystal coexistence is necessary because it removes nucleation barrier. For example, if at the equilibrium this part of crystal infinitely long coexists with this part of liquid, then we can make sure that its temperature is equilibrium melting temperature at this particular pressure. Performing a sequence of such simulation at different pressure and applying a linear fit to pressure temperature axis, we can understand that first, this line is related to Clapeyron equation, but second, and it's most important, at zero pressure we can reliably define the equilibrium melting temperature at normal conditions. Also, Clapeyron equation involves other thermodynamical properties that can be defined from a different constant pressure, constant temperature simulation. In particular, at a certain temperature, we can choose such a lattice parameter that the established pressure after distribution of this temperature will be zero, so normal conditions. Of course, with the heating of the crystal, the material will respond to this heating by means of thermal expansion, and lattice parameter will increase. Exactly from the same modeling, we can also put the points which correspond to the energy per atom given by this temperature. So we can continue performing such simulation until the crystal exists, until the crystal spontaneously goes to liquid. But then we can perform the same kind of simulations for liquid, lowering the temperature. And if we now apply a dashed line corresponding to the equilibrium melting temperature at normal conditions, defined from the previous liquid crystal coexistence simulation, then we can understand that this jump between solid and liquid lines for lattice parameter corresponds to volume of melting, and this jump for energy per atom corresponds to enthalpy of melting. Moreover, the slopes of this line is related to linear expansion coefficient, and slope of this line is related to heat capacity. That's how we can determine all the thermophysical properties given by this interatomic potential and collect them in a single table and compare with what is given by the experiment. From this table, we can see that number of parameters pretty much well reproduced, but some of them are not reproduced, where the difference can be as much as 20%. It doesn't mean that we cannot use this potential to study the kinetics of phase transitions, but it just means that when quantitatively characterizing our results, we must keep in mind that we are not modeling real nickel material, but it's some different nickel, little bit artificial. So we apply this knowledge to study first is a homogeneous nucleation process occurring inside of bulk. Here's a sequence from simulation on homogeneous melting. The nuclei of new phase is shown by different color, and the solid phase is not shown, but it's present. So in this animation, one can see that at a certain temperature, nuclei appear with a certain frequency, they grow, and the nucleation barrier overcame, the nuclei continue growing, and coalesce in a large volume of new phase. In a similar way, we can study heterogeneous classical melting propagation when the solid-liquid interface already exists, so there is no nucleation barrier anymore, and it can propagate as the heat provided, propagate with a certain velocities and giving us the necessary kinetics. So this animation of the heterogeneous melting process. Solid, the top is not shown, we show only liquid, and the solid-liquid interface propagates. We also see that it fluctuates, but nevertheless it keeps more or less planar shape. So now we can move towards laser matter interactions. And first thing that we can have problems with is that, unfortunately, for pulses shorter than characteristic electron-phonon equilibration time, which is on the order of 1 to 30 picoseconds, for pulses shorter, the presence of free carriers that are absent in classical molecular dynamics, the presence of those carriers becomes essential. Namely, it is free carriers that absorb the laser energy, so the rising temperature as a function of time on the surface. The free carriers absorb the laser energy for surface and for rare surfaces, and only then, by means of electron-phonon scattering process, during the electron-phonon equilibration time, these free carriers gradually pass the kinetic energy to phonon vibration, so increasing therefore lattice temperature. And then they come to equilibrium. So therefore, ultra-short laser pulse interaction processes with classical molecular dynamic approach is not possible to model because we, on purpose, discard the information about free carriers. So the idea, therefore, is to account, not explicitly including these free carriers into molecular dynamics description, but to account on the effect of these carriers' presence. How it's done? So on one hand, we have molecular dynamics method, which is governed by second law of Newton. And it is just this system of differential equations that we solve. On the other hand, we have so-called two-temperature model, which assumes two subsystems that interact with each other via electron-phonon coupling. The subsystem of electrons having temperature of electrons, and subsystem of phonons having temperature of phonons. So these subsystems interact with each other, and this two-temperature model can describe laser energy absorption, fast electron heat conduction, and laser-generated electron-phonon non-equilibrium. It looks like the energy balance between electron system and phonon system, describing heat transport, energy exchange, laser absorption, and it's actually two differential equations standing for electrons, diffusion equations standing for electrons and for phonons. And they coupled via the electron-phonon coupling. So on one hand, we have molecular dynamics method, which can address the kinetics of non-equilibrium phase transitions with atomic resolution. But on the other hand, this molecular dynamics method is missing free carriers, so it cannot be used for the case of ultra-short laser pulse interaction. On the other hand, we have two-temperature model, which is in continuum via electron-phonon temperature dynamics, describes fast electron heat conduction, electron-phonon non-equilibrium, laser light absorption, but realized in continuum, it cannot describe non-equilibrium phase transitions because of high temperature pressure gradients, significant degree of overheating, and small nuclear, new phase nuclear sites. So therefore, the idea is to unite the advantages of this method in the scale of a single computational approach, so that we completely substitute the equation for phonons into temperature model with molecular dynamics integration. And the electron-phonon coupling is directly accounted for in the molecular dynamics via additional friction term. But this friction have a negative character. So therefore, the electrons described in continuum, we divide our space to number of cells. Each cell corresponds exactly same volume in molecular dynamics domain, and each cell has its own temperature, and then we accumulate the energy coming from hot electrons and redistribute this energy among the atoms, allocating exactly in the same volume. So that's how it works in a simple representation, and with this atomistic continuum combined approach, we can finally study ultra-short laser interactions with metals. So we can identify the laser light absorption, we can model fast electron heat conduction process, we can also address electron phonon non-equilibrium and equilibration process during the electron phonon equilibration time. We can study processes of melting, spallation, ablation processes, evaporation. And now, using this numerical tool, we can try to address the problem of nanostructuring process. So these are nanostructures obtained at laser centrum Gannover. Depending on the applied fluence, applied energy of fluence, the aspect ratio of the structure changes. These structures are very repeatable, reproducible, and very sensitive to the applied fluence. So we are going to study the mechanism of these structures in order to learn how we can manipulate with the final properties of the obtained structures via the irradiation parameters. So first we model the smallest possibly obtained structure with a nanobump. In order to model this structure, we apply the molecular dynamics domain only around the structures, and the rest space will be modeled in continuum. And even though we only apply small region, we only investigate small region with molecular dynamics, it still consists of huge number of atoms. It can be several billions of them. So therefore, performing such simulation with a single processor approach is no longer possible, and we have to use multi-processing regime via utilization of message passing interface library. So we divide our region, this is top view, to number of cells. Each cell will be governed by a single processor, its own processor. Each processor volume is divided to mesh, two-dimensional mesh, inside of which we solve simultaneously combine a continuum atomistic method. So we solve in three-dimensional case diffusion process, laser light absorption, and non-equilibrium directly accounted in a coupling with molecular dynamic representation. And because, and this is how the connection between different processes looks like. So the system is divided to a number of processors. For example, each processor knows exactly all the information only inside of the borders with a red color here. But for calculations of forces acting, for example, on particle 25, we have to consider interactions with neighboring particles belonging to other processors. So therefore, the processor knows everything inside of red borders, plus a little skin layer around it. And this is all. This is all. It's limited only by this volume. Therefore, this processor doesn't even know about the size of the system. So it can be, therefore, with this approach, one can model infinitely large system, and it's only approach limited by the computational power in your possession. And the message passing interface is schematically depicted here. So processor 1 knows everything about only these particles. And if on the next time step the sum of particles cross the border of the processor, all the corresponding information is sent to the corresponding neighboring processor. Applying advanced linked list algorithm for composing the neighbor to list of interactions, so-called neighbor list, we reduce the number of operations to n over 2, where n is the number of particles in the system. And we broke eventually the Amdahl's law, which was proposed a few decades ago, and it's declared that even with infinite number of processors, it's impossible to reach speed up in calculation more than 100 times, because of the presence of so-called sequential part, which is not possible to be written in a parallel version. But due to reorganization of all this neighbor list search and message passing interface, we removed this sequential part and succeeded even in superlinear scalability of the speed up process. So we can now operate with extremely large systems, and we can now come back to a nanostructuring process. So we studied this nanostructuring process because there was a number of proposed theories what is the mechanism of this nanostructure growth. Among them, there was a theory proposing that the nanostructure grow due to pressure of evaporating material between the film and the substrate, or it can be Marangoni effect, or it can be capillarity and gravitational forces. So, and this is the this is the answer what our simulation gave us. So we simulate the 200 femtosecond laser pulse interacting with circular slab of molecular dynamics domain, and the rest is described in continuum. So these are simulations from this modeling. So each atom, each dot is representing atom. The atoms are colored by the potential energy, so that we can identify solid and liquid. This is liquid, so this is solid. Surface atoms. You can also see a formation of dislocation place due to rapid expansion of the central part of the film. Then the film solidified. So film is situated on imaginary substrate. So this is first simple and a little bit scaled down simulation subject to determine essential mechanisms responsible for the nanostructuring process. In order to identify the mechanism of the nanostructuring process, we will monitor the dynamics of pressure evolution and velocity of liftoff of molten material in the very central part. So it is presented here. So this is velocity of lift of the material in the vertical direction as a function of time. This is pressure evolution as a function of time in the central part of the material. So what we can notice is that acceleration of the molten part of the material in the vertical direction takes place completely due to propagation of the first strongest pressure wave. So how it happens? We can understand if considering rate of heating and mechanical relaxation. So the heating rate is determined by either pulse duration or the electron phonon coupling time, whichever is greater. So in our case, the pulse duration, 200 femtosecond, much shorter than the electron phonon relaxation time, about 10 picoseconds. So the heating rate is determined by the time of heating, 10 picoseconds. The mechanical relaxation rate, basically it is attempt for material to expand in response to that heating by means of thermal expansion. So in our case, the heating rate exceeds the rate of material expansion in response to that heating. So we heat the material faster than material mechanically relaxing. That's the reason for accumulation of huge compressive stresses inside of the material due to this fast heating. These stresses eventually will relax with the propagation of pressure wave with a sound speed on the distance corresponding to efficient heating depth of the material with this laser pulse. So if this inequality holds, it's called internal stress confinement regime, and it means that this regime is favorable, therefore, for nanostructuring processes. That's why, as a result of extremely fast heating in the middle part of the material, we have an accumulation of high compressive stresses that relaxed with the propagation of very strong pressure recoil, which causes the acceleration of the molten part of the material, which already has zero shear modulus, so shear stresses. So the liquid easily picks up the momentum accompanying with the propagation of the pressure recoil and accelerates in upward directions. That's the mechanism of the nanostructure growth, so the relaxation of laser-induced stresses responsible for the nanostructure growth. On the other hand, let's see how this structure solidifies so fast. For that purpose, we plot electron and lattice temperature on the same plot as a function of time in the middle part of the material. We see that electron first picks up the laser energy as they must, and then during the electron phonon equilibration they come to equilibrium. So after 10 picosecond, the temperature of electrons and lattice equal. But then, due to extremely fast electron heat conduction in three-dimensional space, the temperature of electrons goes even below the lattice temperature, providing therefore already cooling for the molten material and act as efficiently as a freezer. And therefore, that's the reason for fast solidification of this growing nano feature. When having these two essential mechanisms determined, so growing of nanostructures is governed by relaxation of laser-induced stresses, and solidification is governed by fast electron heat conduction in three-dimensional space. We can simulate the nanostructuring process already on the experimental scale. For example, we can now simulate the nanobarrier structure formation on real experimental scales. For that purpose, we take this elongated brick of the material. We also realize that there are no temperature or pressure gradient in one of the direction, x direction. Yeah? So we therefore have this computational cell schematically shown here. So we have molecular dynamics domain situated on silica substrate covering 5 micron of experimental scale. We also model only 5 microns with a combined model, and then up to 50 microns away we provide a heat flux, but described in continuum because no phase transitions occur at this distance. So we apply flat top pulse of 200 femtosecond duration, and we see what happens. So this is side view. It's only small part of the molecular dynamics is shown here, so it's only 2 microns shown here, central part. The atoms here colored by symmetry parameter, so that we can identify liquid from crystals. So we can observe here process of melting. We can also see some propagation of melting along the dislocation planes. The dislocation resulting from rapid expansion of central part of the film increase the potential energy of atoms constituting these dislocations, and therefore melting easily propagates along these dislocations. We also observe elastic plastic deformation, and we see how the structure slowly elevates above the substrate. The next slide, we can see lattice electron temperature interplay. Electron first picks up the laser energy, then due to electron phonon coupling, they gradually pass the energy to lattice vibration. Rapid lattice heating results in relaxation of laser-induced stresses, resulting in a multiple reflection of pressure wave. As pressure wave reflects a number of times, it fluctuates, also causing fluctuation in temperature, and temperature fluctuation of lattice also cause fluctuation of temperature of electrons. So it's a feedback between lattice and electronic system. So eventually, the energy that was put in this system was a little bit high, and by the time of almost 2 nanoseconds, we reached the situation of thinning of the material at the place where solid and liquid is connected, and the material is going to fly away, which is basically a mechanism of spallation. So spallation is a particular case of ablation when we have a removal of material via big, large chunks without formation of any vapor. Vapor is not seen here, as you can see, so it's really mechanical rupture of the material. So this also happens in this experiment, as you can see, and if apply a little bit higher fluence, this droplet can fly away and even caught by a receiver glass that we can put at top of the structured surface. So eventually we can see that we reproduce basically the experiment, and also noticeably that we have formation of nuclei of new solid phase just inside the liquid, which means that the temperature of this liquid is much below the equilibrium melting temperature because of nucleation barrier, and it was overcame. So the solid nuclear overcame nucleation barrier, means that temperature below the equilibrium melting temperature, and it will be solidified. Even if it flies away, it will be solidified. Okay, so now we can step towards periodic nanostructuring, or in other words, functionalization of the surface, since it's very technologically important. So this periodic nanostructuring experimentally was succeeded in laser laboratory in Göttingen with a mass projection setup, which split the laser beam to a number of diffraction orders. Only first diffraction order was selected, and this Schwarzschild objective, it was focused back on the material surface. As a result of interference of these two beams, we succeeded in redistribution of the laser intensity sinusoidal type. And as a result, this kind of periodic structuring of the surface inside of laser spot diameter of 40 microns was succeeded. Depending on the applied fluence, these structures have different quality and aspect ratio, and we are going to investigate the mechanism of the formation as well. So for that purpose, we also identify geometry of the experiment. So first we utilize periodicity in one of the direction. Then we also understand no temperature pressure gradients here, so we can also apply periodic boundaries here. And we resolved atomistically only the region, pre-surface region of the material, where most intensive processes, including phase transition, can happen. So at a certain depth, which was here like 200 nanometers, below this depth, there are no phase transition processes, therefore it's not necessary to resolve it with expensive numerical molecular dynamics calculations. So we placed specifically behaving non-reflective boundary conditions here, which imitates the presence of the material below and the pressure wave resulting from the relaxation of laser-induced stresses penetrates this boundary without reflection. And this boundary also transparent for the heat flux. This heat flux is provided up to 50 microns below the surface. So now we have the sequence of snapshots, atomic snapshots from this simulation in order to visualize the process of periodic nanostructure formation. So we only show a little structure formation here, but it corresponds to reproduction of this periodicity at the end of the simulation. So atoms here colored by central symmetry parameter. Depending on the value of this parameter, we can identify atoms having crystal structure, participating in the crystal defects, dislocations, liquid, surfaces, and vapor atoms. So we can see that we have fast melting established, melting front propagates, and then at some point we can see formation of voids. These voids, as you can see, empty on material, so there are no vapor inside. It's not a boiling process. It's a rupture, mechanical rupture of the material due to relaxation of huge laser-induced compressive stresses, internal stresses. So these are really a vacuum inside, and you see how these voids coalesce and the structure grow eventually. We can also see how many dislocation planes propagate, resulting from rapid expansion of the central part of the material. And at some point you can notice formation of nuclei of new solid phase inside of liquids, so this structure therefore already significantly undercooled by that time. And finally it solidifies, having of course polycrystalline character, because those nuclei of new solid phase have of course random orientation. So this final structure has a polycrystalline character, and it's reinforced with a number of dislocations, because formation of dislocation increase the endurance of the material. It works like forging of iron. So it's a process is called laser pinning, and its purpose to create a lot of dislocation to increase its hardness. So the formed nanostructure have high endurance and high hardness. When comparing with the experiments, we can identify that not only qualitatively but quantitatively we reproduce the formation of these structures. So these cuts from the experimental pictures were prepared with focused ion beam method, and by means of transmission electron microscopy we can see that the voids formed inside, this is gold, and even this voids, depending on the applied fluence, can have different shape. We now can show you simulations at the higher period between the structures, so, and a little bit higher fluence. So you can now identify already vapor atoms, but not significant amount. Then the structure grow to higher aspect ratio. We can also identify beginning of solidification. And we were lucky here that we just decode the moment of onset of spallation. So this spallation means that the momentum of the motion of the tip of the forming structure is still high, and even though the solidification process is ongoing, it's not enough to stop this momentum, stop the motion of structure in upward direction. And eventually the crack propagates across the structure and the tip will fly away. It noticeably when considering field of lift-off velocity. So now color means velocity of lift-off, velocity of motion in upward direction. You can see that bottom structure has 0 velocity, however tip of the structure has some kind of non-zero, some 100 meters per second velocity. The temperature field also shows that the bottom of the structure quite cooled down already, and even tip of the structure which is flying away have temperature significantly below the equilibrium melting temperature. So it will be solid when it spall. And at high fluence we can observe how the structure forms, and we now have significant amount of induced vapor. The dislocations grow in a much larger amount. The nucleation of internal voids, now the voids also contain vapor inside, but this vapor still has a little effect since the momentum of motion of the structure up in upward direction is really high here. So the structure opens up to the surface at some moment, which also corresponds to the experimental conditions and this applied fluence. So and now we can understand why we have merging walls of the nanostructures, periodic nanostructures at high fluence. So if you now plot the field of velocities in tangential component, so it's velocity in y direction, color means velocity, so we can see that the left walls move to the left and right walls move to the right. So that's the reason that if structure opens to the air, it can most likely merge with the neighboring walls of growing structures. So this same situation happens at higher period, which allowed us to match the theory and experiment. It means that we, by means of reproduction of the structure, we basically reproduce what happens in the experiment. And it means also that we have created a very powerful numerical tool in order to not only study the mechanism of those structures formation, but also use this numerical tool to design the experiment for generation of structures with demanded properties, so that we can give specific surface properties, we can functionalize surface in the way we need, in the way we want. And I don't think I have enough time for plasmonics, so I will try to fit only the nanostructuring underwater. So the idea is that experimentally it was detected that nanostructures generated in water, they have cleaner character and they have finer dimensions. So it seems like experimentally it was detected that it seems that the water has a good effect on a nanostructuring process, and we will try to understand why. For that purpose, we apply pretty much same model for metal water system. So we place a water layer atop of the material, atop of metal. So water here, although having 3 particles, is represented by a single particle. The reason is to keep high efficiency of calculations. Instead of 3 particles, we only process 1 particle. Of course, in this case, heat capacity is underestimated. But what we believe is that most heat losses occurring during the cooling of the growing feature will be due to heat of vaporization, which is much more higher than heat capacity consumed by heat capacity process, heat capacity value. So the water, all the system is divided to a number of cells. Each cell will be governed by a single processor. Each cell is divided to 3-dimensional mesh, so we resolve normal molecular dynamics classical approach for water. However, interatomic potential here, it's embedded atom method, and it reproduces very well the mechanical properties of water, although not all thermal properties, of course. So the metal will be treated with combined atomistic continuum model, and below non-reflective boundary conditions, when no phase transition occurs, we can apply only continuum approach, describing heat flux, providing cooling for the surface part of the material. So we also apply geometry of the experiment, and now we can compare what happens in air or in vacuum and what happens in water. It's exactly the same experiment, exactly the same irradiation parameters. The only thing that in this on the right, you will see water layer reflected by green color. So again, we color the atoms by center symmetry parameter for identification of crystal, defect structure, surface, vapor, and so on. So now we have exactly at the same time, we have corresponding snapshots from two systems. So we can see that initially we have similar melting process, but then we notice that first we have onset of evaporation along the metal-liquid interface, and also formation of a shock wave inside of water because of a rapid expansion of the surface. Then we have formation of voids in a similar way, but already by 50 picosecond we notice that water has additional resistance on growing nanostructure, and therefore the structure grows slower. And additional resistance of water is also reflected in the way that the dislocation planes penetrates deeper, and the formation takes more massive character. And also we can see that developing evaporation process along the metal-liquid interface has a profound effect from a point of cooling of a growing structure. So the structure grows slower, additional resistance results in the thicker walls of the growing structure, and it cools down faster. So eventually, you can see that the structure takes very right shape, very correct shape, unlike the structure growing in air. And the solidification process is also faster. So already now, the structure is almost solid. This one solidification process just started. You can see it by appearing blue nuclei inside of light blue color. So eventually, the structure is solidified, and the structure in air has broken to the air. And even at higher fluence, the structure underwater still intact, still have its integrity, but structure in air completely open to the air with production of number of debris. So this modeling in water therefore confirmed the situation that the water has a profound effect on nanostructure growth. It has a significant cooling effect. We can study how the mechanism of nanostructure grow occur in water. So this water here as well, but we just don't show it, which allows us to have a visual analysis of the growing feature depending on the applied fluence. And here's the interesting result that you see the onset of boiling process occurs exactly what is predicted by thermodynamics, so where the largest contact area occurs. So as a result, we can say that the structures produced underwater smaller, they have thicker walls, they kept integrity, dislocation produced under the structure increase its hardness. We have no debris formation and faster formation due to evaporation. So that's probably all. 55 minutes. So I need, either I have 15 minutes more or I can stop
you
here.
have 5 minutes still.
But it's no reason to start the topic if it requires 15 minutes.
Yeah, but you have 5 or 10 minutes if you want.
Okay, then let's maybe cover it fast. So, plasmonics. How to include plasmonics? Basically, we want to model laser-induced periodic surface structures, LIPS. That's example of plasmonics. These are examples of plasmonics in technologies. So in surface-enhanced Raman spectroscopy, metamaterials design, catalysis, subwave imaging, and these are LIPS that were produced with experiment, depending on the pulse geometry. And there are LIPS, these LIPS produced in multi-pulse regime, but there are also LIPS produced with a single pulse, which we will begin our study with. So The production of LIPS can change morphological properties, hydrophobic properties, optical, magnetic properties of the material. So we want to learn the mechanism of this LIPS formation in order to design the corresponding experiments on material surface functionalization. So the common understanding of the LIPS formation comes that, okay, if we have just a flat surface of material, the incident Gaussian wave results in nothing, just the absorption. But if we have a step or defect or any other point resulting in a local electron density jump, then the incoming electromagnetic wave can result in excitation of collective motion of electrons in this place. And collective motion of these electrons and propagation corresponding wave results in the propagation of so-called surface plasmon polariton, propagating along the interface between two different media. So this surface plasmon polariton interferes with the incident electromagnetic wave, resulting in the modulation of heating of the sample surface. So the intensity, absorbed intensity is redistributing across the surface, and that's resulting in modulation of heating. So, of course, the natural place to include plasmonics seem to be in continuum description of free carriers dynamics, which is a part of the combined atomistic continuum model. So, continuum description is a term, is a source term entering the continuum description of electrons. In the multipulse regime, of course, the feedback between new obtained surface and absorption of new laser pulse must be accounted for. So in a simpler way, without surface plasmon polariton, the source term entering to temperature part of the combined model is quite simple. And this intensity can be described with depth in a simple manner. So it's Lambert's-Beers law, and this is Gaussian profile in time. But in the case of surface plasmon polariton excitation, we must account for the knowledge of electromagnetic field, and that's possible by means of constructing Poynting vector, divergence of which will give us this source term. So the electromagnetic field is decomposed to the paths provided by laser radiation and surface plasmon polariton excitation. So now all components of electromagnetic fields are accounted for, and the new source term will look much more complicated. So it has laser, plasmon, plasmon polariton, plasmon inputs, and the first attempt to build how the laser energy will be absorbed was quite successful. So this is the intensity redistribution in depth and lateral distance for the case without surface plasmon polariton excitation and with. And the modulation is actually a function of wavelength. So for shorter wavelength, as you can see, the decay of this modulation is much faster. So we will work with a shorter wavelength from the point of molecular dynamics because it's just more efficient. So let's see how the energy is absorbed without surface plasmon polariton and with, without and with at top. So during the pulse evolution, so now pulse is 200 femtosecond, and during the pulse evolution we can see that unlike the planar wave, inclusion of surface plasmon polariton results in the energy absorption redistribution. So we will compare our modeling results with experiment. So in experiment on gold surface there was a scratch done, and we will model this brick with the material assuming the step at the middle, and this is a side view of our computational system. So this is molecular dynamics domain, the atoms colored by central symmetry parameter as usual. We zoomed a little bit the atomic structure and temperature field of phonons, so lattice temperature field in this window. So as pulse propagate, we can see that we have modulation and heating, but the energy that was applied was too high. So now the structures, as you can see, breaks and open up to air with significant amount of vapor. So first attempt failed in formation of LIPS, so we had to decrease the incident energy. That was quite successful this time. So now the fluency is lower, we have a gradual melting process, already noticeable modulation, and now the accurate small structure growing in the same manner as it was defined above as a mechanism of nanostructure growth, and eventually they solidify to quite nice structures with a fast decay, 5 periods, which exactly corresponds to the experimental measurements that were observed. These are experimental images, so we can see that these structures, these leaf structures, they form parallel to the step edge, and the comparison with the experiment, or the comparison of numerical results with the experiment was quite good. So we matched with high precision on periodicity and on the length of the structure decay. So this picture again demonstrates that these kind of leaves appear at the step edge structures. Yeah. So to conclude, we included the effect of pseudophilus plasmon polyelectron excitation into combined atomistic continuum approach. We investigated how this pseudophilus plasmon polyelectron results in the energy absorbed from the redistribution. We modeled leaps, and we were successful on matching the experimental measurements with the results of modeling. Thank you very much for your attention.